Now I'm
Hello.
going to present my screen. Can you see my presentation?
Yes, very nice. Thank you.
Thank you. Well, ladies and gentlemen, a short report on the results of research on the topic A Secure Cloud Computing Approach for Rapid Implementation of Public Key Cryptography on IoT Terminal Devices is presented to your attention. The permanent improvement of Internet technologies and integrated circuits determines the rapid development of the Internet of Things concept and the active expansion of its practical application areas. Some of the most significant areas from a security point of view are shown on slide 2. Among them, we can highlight security alarms and intelligent video surveillance, remote health monitoring, process control, environmental quality control, as well as control of unmanned vehicles using Starlink technology. The basic idea of the Internet of Things concept, as illustrated on slide 3, is to use the network as a data exchange environment in remote control systems for real-world objects. This creates a number of advantages, which are shown on slide 4. At the same time, there are risks associated with the use of the Internet in remote monitoring and control systems, and the main ones are presented on this slide. One of the most critical is information security threats, which is highlighted here. Such threats fall into 3 main categories, as shown in the same slide. Among these categories, the possibility of falsification monitoring data, as well as commands sent from control devices, appears to be the most critical and requires careful protection in the process of confirming the integrity and authenticity of the data. Public key cryptography, in particular digital signature mechanisms, is traditionally used to implement such protection. The basic computational operation in such cryptography is modular exponentiation, performed on a large bit numbers. The NIST recommends the bit depth of these numbers as 4096. Obviously, this significantly complicates the implementation of modular exponentiation in real time on a low-power microcontroller, as required by most areas of remote control systems. In theoretical terms, there are 3 possible ways to increase the performance of modular exponent calculation on terminal platforms. The first of them is to use cryptoprocessors. The second way to speed up modular exponentiation is to switch to alternative algebraic bases, for example, to the algebra of Galois fields. And the third way to increase the performance of modular exponent calculation is to involve cloud computing, which is possible due to the presence of a radio modem in the terminal microcontroller. In this case, it is necessary to make it practically impractical to reconstruct secret elements of public key cryptography from data transmitted to cloud systems. Today, the last of the described methods is suitable for practical application. And that is why the largest number of scientific publications are devoted to the development of this particular direction. All existing solutions based on the involvement of cloud systems in the calculation of the modular exponent on a terminal microcontroller can be divided into two groups as shown on slide 7. The first of these consists of methods that use the capabilities of remote crypto processors. Such solutions are characterized by high speed with the impossibility of obtaining intermediate results, which prevents the effective organization of distributed computing between the terminal and remote platforms. The second group, accordingly, includes methods that do not involve the use of crypto processors, and these methods are based on the use of high-power processors of remote computer systems. This allows organizing the effective distribution of computing between the cloud and the terminal microcontroller due to the wide exchange of data between them. In system plan, the efficiency of such methods is assessed by two criteria: acceleration of the implementation of modular exponentiation on the terminal microcontroller due to the use of remote computing, and the level of protection from malicious attempts to reconstruct the secret components of the operation based on the data transmitted to cloud systems. The first of the criteria is generally determined by the ratio of the total number of n bits of the exponent to the number of NMC bits that are processed on the microcontroller in methods involving cloud systems. The second criterion is determined by the volume of the search that must be carried out to restore the secret NMC bits of the exponent code. It is quite clear that both indicators depend on the number of NMC exponent digits that are processed on the terminal microcontroller. Thus, increasing the efficiency of modular exponentiation in known solutions is actually a search for a compromise between the acceleration of this operation and the level of security of calculations. This compromise can be resolved in two ways: by reducing the processing time on the microcontroller of a separate bit of the exponent code, and a more complex logical organization of the distribution of calculations between the cloud and terminal platforms, which will ensure an increase in the volume of enumeration with an unchanged number of NMC bits. It is the latter of these ways that forms the basis of the study offered to your attention. The aim of the study is formulated accordingly, presented on this slide. The proposed method is a development of the concept of multiplicative additive decomposition of the secret exponent code E, which is widely used to accelerate the calculation of the exponent with the involvement of cloud systems. The number L of secrets for the cloud bits of the exponent is determined by the sum of the bit depth of the components U and W processed on the microcontroller. But at the same time, the cloud doesn't know the specific values of these lengths, and it has been proven that it is due to this that the volume of search N1 for the intruder to select the values of U and W with unknown results of modular exponentiation is determined by the formula presented on slide 11. Thus, the use of a multiplicative additive decomposition of the code E allows, due to the increase in the volume of search for illegal recovery of the code E in the cloud, to increase the level of security by L plus 1 divided by 2 times compared to the 2 to the power of L. Based on this, an idea arose to further increase the level of protection without increasing the number L, to use more complex forms of multiplicative additive decomposition of the exponent code. As a first step, a two-component multiplicative additive decomposition of the exponent code was investigated, which is shown on slide 12. The components of the exponent code processed on the microcontroller are marked in red. Their total length is equal to L. Below, it is proved that the volume of search N2 and therefore the level of security is determined by the formula presented on this slide. For example, for L equals 120, the value of N2 equals to 1815 multiplied by 2 to the power of 120, while for the traditional multiplicative additive decomposition of the exponent, the volume of search N1 equals to 60.5 multiplied by 2 to the power of 120, and for the usual additive decomposition, it is 2 to the power of 120. The next slide shows the diagram for obtaining the dependence of the number of search options on the value of L for a two-component multiplicative additive decomposition of the exponent code. If you have any questions regarding to the technology of mathematical proof, I'll be happy to provide detailed explanations. As a next step, a three-component multiplicative additive decomposition of the exponent code was investigated, which is shown on this slide. By analogy with a two-component decomposition, the total length of the components U1, U2, U3, and W processed on the microcontroller is equal to L. Below is the proof that the corresponding search volume N3, that is the level of protection, is determined by the formula presented on this slide. With a three-component multiplicative additive decomposition for L equals 120, the volume of search N3 equals 36,905 multiplied by 2 to the power of 120, which is 20 and 610 times greater than the same indicator for a two-component and traditional one-component multiplicative additive decomposition, respectively. Accordingly, compared to the usual additive decomposition of the exponent, the use of a three-component multiplicative additive decomposition allows increasing the level of security by 36,905 times. This slide shows a diagram of obtaining the dependence of the number of search variant on the value of L for a three-component multiplicative additive decomposition. If you have any question regarding the technology of the mathematical proof, I'll be happy to provide a more detailed explanation. Similar to the first two levels, the general case of M-component multiplicative additive decomposition of the exponent code was investigated, but unfortunately the volume of the conducted research doesn't allow them to be fully displayed within the format of a short conference report. However, the general nature of the dependence of the security level on the number of components of multiplicative additive decomposition is presented on slide 16. In conclusion of this report, the main findings of the study are briefly presented on slide 17. And that's all for now. If you have any questions, I will be happy to answer them. Thank you for your attention.
Thank you very much. Please, have any questions? Very nice. I have a small question, Maria. Thank you for your presentation. It was very useful for us and very interesting. Have you made any evaluation to the known methods about to the performance of your methods for Internet of Things implementations?
Thank you for your question. Maybe you can repeat it more slowly or
Yes,
slowly
yes,
because
yes.
it's
Had you made any comparing research with the known another types
solution, other
of
solutions. Yes.
yeah, other solution? Yes, and have you any results on that?
Okay, thank you for your question. Well, if we talk about other solutions in this area, we can say that the methods of secure modular exponentiation proposed to date assume additive or additive multiplicative expansion of the exponent code E. In known methods, the level of security is strictly limited by the requirements for the time efficiency of calculations. Unlike the known methods, our approach allows to increase dynamically the level of security depending on the specific practical application, while leaving the speed of implementation of modular exponentiation unchanged. And this effect is achieved precisely due to the multi-component of multiplicative additive expansion of the exponent code.
Thank you, Arias. So, what the length of your bits of your numbers that you make the explanations? Because nowadays we need to have about more than 2,000 bits, about 4,000 bits. It's a new,
Yes,
I think,
yes.
yeah.
New standards that NIST recommends today to use the bitness equal to 4096. It's new standards
Yes,
today. And we use this bit length. But for example, in our solution, we talk about, for example, that bit length of the code that is processed on the microcontroller is equal to 120, while the total length of the exponent we leave 4096. 4096.
okay. Thank you very much. Thank you very much for your presentation.
Thank you for your
Please,
questions very
thank
much.
you. Have we any more questions, please? Okay, so let's go to the next one. The next one is 100.